Hello students, myself Dr. Himmat Singh Chawra, Associate Professor, School of Pharmacy, Suresh Gyan, Vihar University, Jaipur. In Physical Pharmaceutics 1 lecture series, we were discussing about the surfacial and interfacial phenomena. In previous lectures, we discussed about the surface tension, interfacial tension, and its measurement. Now, in today's lecture, we have to discuss about the hydrophilic, lipophilic balance, determination of detergency, and concept of solubilization. These are the topics of today's lecture. So, after the completion of today's lecture, the student may be able to know about the HLB determination methods for surfactants. They know about the how can we determine the hydrophilic, lipophilic valence value, know about the detergency, what is the detergency and what its mechanism, how it is applicable in pharmacy. Then very important process which is known as solubilization. So in this lecture we discussed about the what is solubilization, what is mechanism, and then what is the significance or applications of solubilization in pharmacy. These are the different learning objects, and after completion of today's lecture, the student will be know about all these parameters. Now, first of all, starting from the HLB, hydrophilic, lipophilic balance. So, hydrophilic, lipophilic balance, it is a arbitrary scale having 0 to 20 points, which was given by the scientist Griffin. So Griffin gives a arbitrary scale having 20 points to explain the different functions of surface active agents based on their hydrophilic, lipophilic valence value. So it is a scale showing classification of surfactant function on the basis of hydrophilic, lipophilic valence values of surfactants. The higher the HLB of a surfactant, the more hydrophilic it is. Example like spans with low HLB value are lipophilic in nature, whereas the twins with higher HLB values are hydrophilic in nature. So, surface active agents are classified on the basis of hydrophilic, lipophilic valence scale. And once the hydrophilic, lipophilic valence values are more than 10, it can be classified into hydrophilic surfactant. If the value is less than 10, it can be classified as lipophilic surfactant. And very common example of lipophilic surfactant is sorbitol esters, which is commonly known as spans. And high HLP value indicates the hydrophilicity of surfactants, and common examples are twins, polyoxyethylene sorbitol esters, they having the HLB value more than 10. Both of the spans and twins are non-ionic surfactants. When we go through the HLB scale, we can find the different surface active agent on different values. Like when we compare the different surface active agent based on HLB scale, in most anti-foaming agents having the HLB value 1 to 3. So forming agents are also having the HLB value 1, 2, 3. Similarly, when we go through the weighting and spreading agents, they are also surfactant, but they having the different HLB value, which is 7 to 9. Again, when we go through the emulsifying agent, water in oil type of emulsifying agent, you can find the HLB scale, and the values of water in oil emulsifying agents are 3 to 8. And reverse to water in oil emulsifying agent, oil in water emulsifying agents having more HLB value. In this scale, it is given as 8 to 16. When we consider the surfactant as detergents, which having HLB value 13 to 16, and solubilizing agents having HLB value more than 15. So these are the different examples of surface active agents based on their function and hydrophilic, lipophilic valence value. So particular HLB values are required to function a surfactant for specific purpose. Now, when we go through the determination methods for surface active agents based on HLB values, first we have to find out the HLB value. So how can we determine the HLB, hydrophilic, lipophilic valence value for a given surfactant? So there are different methods based on their saponification number or acid number. So first we have to know about the what is the saponification number of an ester, or what is the acid number of fatty acid. So number of milligrams of potassium hydroxide required to neutralize the acid is acid number. And to saponify the ester, this is the saponification number. So first one is the determination of HLP for polyhydric alcohol fatty acid esters like glyceryl monostearate. So for determination of HLB value for polyhydric alcohol fatty acid esters, formula is given here. HLB equal to 21 minus S by A, where the S is the saponification number of the ester and A is the acid number of the fatty acid. So when we put the value of saponification number of the ester and acid number of the fatty acid, we can determine the HLB value for polyhydric alcohol fatty acid esters by the formula HLB equal to 21 minus S by A. Second method for determination of HLB, this is the surfactants with no saponification number like beeswax and lanolin. So if we want to determine the HLB value for surfactants with no saponification number, we have to use the another type of formula. The formula is given here. HLB equal to E plus P by 5. In this formula, the E is the percentage by weight of ethylene oxide. P is the percentage by weight of polyhydric alcohol group in the molecule. So surfactants with no saponification number like beeswax and lanolin can be determined by another formula which is given in this slide, like HLB equal to E plus P by 5, where E is the percentage by weight of ethylene oxide and P is the percentage by weight of polyhydric alcohol group in the molecules. Surfactant with hydrophilic portion have only polyoxyethylene group or non-ionic surfactant. Then how can we determine the HLP? So the formula can be modified, and the final formula for these type of surfactants with hydrophilic portion having polyoxyethylene group like HLB equal to E by 5. So where E is the percentage by weight of ethylene oxide. So these are the some of the formulas for determination of HLB value. Structure of the surfactant is divided into different component groups. Each group is assigned a number. The addition of these numbers for their respective groups permits the calculation of its HLB value. This is the another method for determination of HLB value. So the formula is given here. HLB equal to E hydrophilic group number minus E lipophilic group number. So this is the another method for determination of hydrophilic lipophilic valence values for different type of surface active agents like CS3, CH2, 11, SO4, Na. So SO4Na having the number 38.7, CS3 having the value 0.475 and CH2 having value 0.475 again. So HLB can be determined with the help of the formula 38.7 minus 0.475 multiplied with 12 plus 7 equal to 38.7 minus 5.7 plus 7 is equal to 40. So this is the another method for determination of surfactant. So surfactant can be classified on the basis of hydrophilic, lipophilic valence values and particular surfactant which show particular function can be categorized in a scale or on a arbitrary scale which was given by Griffin, which is known as HLB scale, hydrophilic, lipophilic valence scale. Now RHLB. RHLB means relative hydrophilic lipophilic valence value. A blend of surface active agent is used in the preparation. When mixing of surface active agent, when more than one type of surface active agents are present, it can be used for relative hydrophilic lipophilic valence determination. So required HLB is critical. HLB is the hydrophilic lipophilic value that is desired in order to prepare a stable emulsion of oil water or water in oil type. So when we go through the emulsion preparation, there is very important method or significant method which can be used for preparation of a good and stable emulsion. Either it may be oil in water type or water in oil type. So on the basis of HLB values, we can prepare a stable or good emulsion of both of the types. The required HLB value is calculated based on the oil phase and the type of emulsion, whether it may be oil in water type or maybe water in oil type. So it is assumed that HLB of mixture of two surfactants containing fraction F of A and 1 minus F of B is algebraic means of HLB values. The formula for these type of emulsions can be known as HLB mix equal to F HLBA plus 1 minus F HLBB, where the HLB of mixture of two surfactant containing fraction F for compound A or 1 minus F for B. So we can determine the required HLB or relative HLB values for different preparations or different surface active agents in blending or mixing also. So this is all about the hydrophilic lipophilic balance value. So it's very important. So when we go through the different functions of surface active agents, we can classify the surface active agent on the basis of particular HLB values. So HLB scale is very important to classify the surfactant based on their functions. Now, the second part of this lecture is detergents. So everyone know about the detergents. What is the detergents? What is detergency? And how it is applicable in pharmacy? And how the surface active agents can play the role of detergents. So detergents, when we define detergents, these are the surface active agents which are used for removal of dirt. So detergents are the chemicals or materials. They are surfactants. They can be used for removal of dirt or debris of the surface. And not only remove the dirt, but they can also useful for providing the shining and glows to the surface. So detergents are the surfactants used for cleaning purpose. Detergency involve the different steps like initial wetting of the dirt and the surface to be clean. So first, the wetting phenomena or wetting mechanism is done in detergency process. So first, when we provide the simple water to the dirt, initial wetting of the dirt and surface to be clean is done. Then after the wetting, the second mechanism is deflocculation and suspension. These particles are deflocculated or separate out or segregated, and then they can form the suspension and emulsification or solubilization of the dirt particles in the done. After it, when we provide fresh water, then final washing away the dirt. So this is the simple mechanism of detergency where the different steps like wetting, deflocculation, emulsification, solubilization, and then finally washing away the dirt. So you can see the diagram here, how surfactant remove the dirt. So the molecules in first the detergents molecule or surfactant molecule been pushing the grease or debris or dirt which is present on the surface. So the molecule insert their hydrophobic tail inside the feed because we already know like dissolves like surfactants are amphiphile or amphiphilic in nature. So their hydrophobic tail insert inside the fat or debris or dirt material, or their hydrophilic part will move apart from the inside. Then after it, there may be the segregation or deflocculation occur, and then solidization of the dirt particles occur. So the polar and hydrophilic heads carry the dirt in the water. The agitation of the fluid make easier the process. And when we provide the fresh water, so solubilization of the dirt particles occur, and then the removal of the dirt can be done easily. So this is the process of detergency. And when we go through a flow diagram here, you can find out the PPT in this PPT where the dirt or glass, fabric, and skin, then addition of detergent, and you already know which type of surfactant can be used for detergency purpose or detergent which having the HLB value between 13 to 16. So HLB surfactants having HLB value between 13 to 16 can be used for purpose of detergent. So surfactants which having 13 to 16 HLB value can be used as detergent. So for removal of dirt on glass, fabric, and skin, etc., first we have to add the detergent solution. Then wetting the dirt present on the surface. First mechanism, as we already discussed, wetting is done. So wetting of the dirt present on the surface. Then removal of dirt if the dirt is soluble. If the removal of the dirt, if the dirt is insoluble, or if the dirt is oil soluble. So there are three parts of removal of the dirt. If the removal of soluble dirt, first it convert into the solution and then it convert into the foam, and when we provide the fresh water, it can clean the surface. Then if the dirt is insoluble solids, so removal of insoluble solids, first it convert into deflocculation of dirt into suspension, then convert into foam, and when we provide the fresh water, they can clean the surface. And if the dirt is oil soluble, first it convert into the emulsion form, then it convert into the foam, and then when we provide the fresh water for cleaning, they can clean the surface. So these are the different process for different type of dirt. Either it may be soluble in water, either it may be insoluble in nature, either it may be oil soluble in nature. So finally, it can convert into a foam, and then it can clean the surface. So detergency is again, when we summarize the mechanism of detergency, we can say that it is a complex process. A number of steps are involved in this process. First is initial wetting of the dirt from the surface, then solubilizing of the dirt, then removing the insoluble dirt is deflocculation particles, with suspending the particles in the detergent solution. After suspending the particle in the detergent solution, removing the oil soluble material and convert into the emulsion, and converting the dirt into foam so as to wash easily. So it is a complex process, and it requires these type of different steps. So this is the mechanism of detergency. Detergents are very widely used. They can use in the cleaning process for different surfaces of different pharmaceutical industries, as well as in the different hospitals, as well as the cleaning of different instruments and equipments also. So they can use for living as well as for non-living things. Now the second, after the detergency, we have to go through the solubilization. So before starting the solubilization, first we have to know about the solubility mechanism, or what is the solubility. So it is very important term, because most of the today's research are based on the increase or enhancement of solubility. So solubility is very important parameter which is directly related with the bioavailability of different drugs. So first, now let us see what is solubility. Then we have to go through the solubilization process. So solubility, it can be defined quantitatively as the concentration of solute in a saturated solution at a specific temperature. So it is the concentration of solute in a saturated solution at a particular temperature. And qualitatively, solubility can be defined as the spontaneous interaction of two or more solutes or two or more substances to form a homogeneous molecular dispersion. So quantitatively, it is the concentration of solute in a saturated solution at a specific temperature, whereas qualitatively, it can be defined as the interaction between the solute and solvent, or two or more substances to form a homogeneous molecular dispersion. It can also be defined as the molecular dispersion of solute in the solvent. So simplified definition of solubility is the formation of the molecular dispersion of solute in the solvent. Now, importance of solubility. So it is important physico-chemical property of the drug. It is an important parameter to achieve desired concentration in systemic circulation. So when we want to achieve the desired concentration in our systemic circulation, first the drug should be soluble. Because until and unless the drug is soluble, it cannot reach into the systemic circulation and cannot show the pharmacological effect. So it is an important parameter to achieve the desired concentration in systemic circulation. Solubility behavior of the drug is one of the important aspects of pre-formulation testing of poorly soluble drug. So when we go through the formulation in pharmaceutical industry or in our laboratory, first we have to study some of the physicochemical parameter under the pre-formulation study. So solubility should be checked at the time of pre-formulation testing of different drugs. Because until and unless the drug is soluble, we cannot go through the bioavailability and we cannot find out the desired concentration in systemic circulation. So this is the very important aspects of a particular drug. Now, what happens or what is the problem, what are the different problems which are related with the poorly soluble drugs or drug having less water solubility or poor solubility. So these are the different important aspects of poorly soluble drugs. They can reduce the drug efficiency. So as the drug is not soluble, they cannot reach easily into the systemic circulation, and they cannot capable to produce the pharmacological or therapeutic effect. So they can reduce the drug efficiency. The second one is the reduced absorption of drug. So when we go through the biopharmaceutics phenomena, we can find that the absorption is related with the solubility. So because if the drug is not soluble, there may be less absorption or reduced absorption of the drugs can be done. Then if the drug is not soluble, may cause adverse effects or side effects. So these are the some of the problems which are related with the poorly soluble drugs or poor solubility of any drug. Now, if the drug is not soluble or poorly soluble or having the less water solubility, there is a very important term which is known as the enhancement of solubility. So, how can we increase the solubility? There are so many methods like co-solvency, solubilization, micellar solubilization, complexation, addition of another solvent which is defined as co-solvent. So ultimately we have to increase the solubility of a particular drug. If the drug having less solubility or not soluble or poorly soluble. So now let us see about the solubilization. So it can be defined as the preparation of a thermodynamically stable isotropic solution of the substance normally insoluble or very slightly soluble in a given solvent by the addition of the component or components by any suitable method. So it is the one of the method of enhancement of solubility. So if the drug is not soluble or very slightly soluble, then by the addition of another component or mixture of components or by any suitable method, when we increase the solubility, it can be defined as solubilization technique. So it is defined as the simple preparation of thermodynamically stable isotropic solution of a substance which is normally insoluble or slightly soluble in a given solvent by the addition of different components or by suitable methods. Now, process of solubilization, when we go through the mechanism, we can find the different steps like the breaking of interionic or intermolecular bonds in the solute. First state which is occur, which can be seen like the breaking of interionic or intermolecular bonds in the solute. Then after breaking of interionic or intermolecular bonds in the solute, there may be the separation of solute molecules to provide space for the solute. And after the separation of solute molecules, they can provide the space for the solute. Then interaction between the solvent and solute molecules or ion can be done. Then molecules of solids break away from the bulk. Then separation of solvent molecules and freely solid molecules is integrated into the walls of the solvent molecule. So this is the process of solubilization. First, there is a breaking of interionic or intermolecular bonds in the solute. Then there is a creation of cavity or space for the solute, then interaction between the solvent and solute molecules, and then the solid breaks the away from the bulk, and then separation of solvent molecules also done, and free solid molecules is integrated or combined into the wholes of solvent molecules. So this is the mechanism or process of solubilization. So, solubilization of poorly soluble drug is one of the most important physicochemical properties for drug development. Since more than one third of drugs are poorly water soluble or water insoluble. So as I told you, if the drug is not completely soluble or not good solubility, having good solubility or having poor solubility or insolubility, then there may be different problems which can be arise at the time of formulation. So it is very important topic or very important mechanism for R&D purpose. In order to prepare a liquid dosage formulation of these drugs, a solubilization technique is usually applied. The most common used techniques are like the adjustment of pH, use of another solvent which is known as co-solvency, then micellization and complexions. So these are the different techniques which can use to enhance the solubility of different drugs which having poor solubility or which are poorly soluble or insoluble in nature. So by the help of pH adjustment, co-solvency, micellization, complexation, and there are so many methods which can be used to increase the solubility of these type of drugs. Now we have to consider only one concept here. This is the micellar solubilization. So surfactant molecules accumulate in the interface between the water and water insoluble compounds. So due to the amphiphilic nature of surfactant molecules, and we know it's very important step that the like dissolves like. So surfactant which having the hydrophilic part as well as the hydrophobic part, so they can dissolve or they can accumulate in the interfaces between the water and water insoluble compounds. Their hydrocarbon chain penetrates the outermost layer of insoluble compound which combine with the water insoluble molecules. Micelles form around the molecules of water insoluble compound inside the micelles core and bring them into solution in an aqueous medium. This phenomena is called as micellar solubilization. So by the formation of micelles are, as you know, these are the aggregates of surfactant molecules. So surfactants, when we add these surfactant into a system, they can orientate towards the interface or surface. And when we add more amount of surfactant, they can form the aggregate, and these aggregates are known as micelles. So micelles can form around the molecules of water insoluble compound and inside the micelle core and bring them into the solution into an aqueous medium. This is the process of micellar solubilization. Now let us see the detailed mechanism of micellar solubilization. So how it is done. First one, the orientate adsorption of surfactant at interfaces. So as we discussed, at the interface or surface which is occupied by the surface active agent. So it is the nature of surface active agent that when we add these surface active agent, they can adsorb on the surface of interfaces. So oriented adsorption of surfactant at interfaces. So as a surface active substance contains a hydrophilic and a hydrophobic portion, it is absorbed as a monomolecular layer at the interfaces. You can see the diagram here where the A part showing the hydrophobic tail and hydrophobic head of a molecule of surfactant, and in this diagram of number B, the surfactants arrange themselves on the water surface like a monomolecular layer of molecules, and inside it is the cells and membranes tied by their hydrophobic tail. As the cohesion of these molecules is interior, so that of the molecules of the water, the surface tension of water is low. So by the addition of surface active agent, the surface tension of the water will be less. So at water-air interface, surface active molecules will be adsorbed at water-air interface and oriented so that the hydrocarbon chains are pushed out of the water and rest on the surface. while the polar groups are inside the water. So perhaps the polar groups pull the hydrocarbon chains partially into the water. This is the orientation of water-air interface. Oil-water interface, surface active molecules will be oriented so that the hydrophobic portion is inside the oil phase, and the hydrophilic portion inside the water phase. So this is the oriented adsorption of surfactant in interfaces. And at low concentration of surface active agent molecules, the hydrocarbon chains of surfactant molecules adsorb at the interface lie nearly flat of the water surface. At higher concentration, so when all the surface is occupied by the surface active agent molecule, and when we add the more concentration of surface active agent, now let us see what happens. So at higher concentration they stand upright because this permits more surfactant molecules to pack into the interfacial monolayer. As the number of surfactant molecules adsorbed at the water air interface increased, they tend to cover the water with a layer of hydrocarbon chains. Thus, the water-air interface is gradually transformed into a non-polar air interface. This results in a decrease in the surface tension of the water. So, when we add the surface active agent molecule at higher concentration, they can decrease the surface tension of water. Now, how micelle can form? So, when the surfactant molecules adsorb as a monomolecular layer in the water-air interface, they become so closely packed that additional molecules cannot be accommodated with each other. So, the polar group will pull the hydrocarbon chains partially into the water. At certain concentration, the interface and the bulk phase become saturated with this type of monomers. And when we add the more amount of surfactant, so these excess surfactants it will begin to agglomerate or accumulate in the bulk of the solution, forming aggregate, which are called as micelles. And the free energy of the system is also reduced. So micelles are the aggregation or agglomeration or collection of the surfactant molecules. The lowest concentration at which micelles first appear is called as critical micelle concentration. So CMC or in critical micelle concentration is the lowest concentration at which micelle formation starts up. So it is the aggregation or agglomeration of surface active agent molecules, and at the lowest concentration at which this type of micelle formation first appear, this is known as critical concentration of micelle formation, or shortly it is known as CMC, critical micelle concentration. At a given concentration, temperature and salt content, all micelles of a given surfactant usually contain the same number of molecules. They are usually monodisperse in nature. For different surfactants in dilute aqueous solutions, this number ranges approximately from 25 to 100 molecules. So this depends on the different type of micelles. So number of surfactants, the range of 25 to 100 molecules, they are agglomerate or aggregate, and they can form a specific type of structure which is known as micelles. The diameters of micelles are approximately between 30 and 80 angstrom. Because of their ability to form aggregates of colloidal size, surfactants are also called as association colloids or amphiphilic colloids. So amphiphilic colloids are nothing but it is the aggregates of colloidal size range of surfactant molecules. Micelles are not permanent aggregates, they form and disperse continually. So this is the random distribution of surfactant molecules in the water. You can see the hydrophilic part as well as the hydrophobic part of the surfactant molecules. After random distribution, if the more surfactant is added, they can aggregate and form the different type of micelles. So this is the random distribution, and after it, they can convert into a specific type of structure which is known as micelles. So surfactant shapes in colloidal solution. So they can be cone-shaped surfactant resulting in the normal micelles, homophagan core-shaped surfactant resulting in reverse micelles with control of their size by the water content, interconnected cylinders, lamellar phase, or onion-like lamellar phase. So there are different shapes of micelles. Either it may be present in the spherical in shape, plain lamellar shape, or maybe different cylindrical shape. So normal spherical micelles in dilute aqueous solutions, micelles are approximately spherical in shape. The polar group of the surfactants are in the periphery and the hydrocarbon chains are oriented towards the center, forming the core of the micelles. In inverted spherical micelles, these type of micelles in solvents of low polarity or oil micelles are inverted. The polar groups face inward to form the core of the micelles while the hydrocarbon chains are oriented outward. Cylindrical and lamellar micelles. More concentrated solutions of surface active agents, micelles can change from spherical shape to either cylindrical shape or maybe in lamellar phase. So these are the different types of micelles. Now, ionic surfactants capable of reacting with compound possessing ions of the oppositely charged. These reactions may bind the surface active ions sometimes with precipitation. The compounds which react with the surface active ions are also changed, and this may be harmful from the physiological or pharmacological point of view. So incompatibility of surface active quaternary ammonium compounds with bentonite, kaolin, talcum powder, and other solids having cation exchange capacity. Whereas anionic surfactants reacts with the cationic drugs like alkaloidal salts, local anesthetics, most sympathomimetic, cholinomimetic, adrenergic blocking agents, skeletal muscle relaxants, antihistamines, many tranquilizing and antidepressant agents cause precipitation of the drugs lose potency or bioavailability. So drugs with carboxylic, sulfonic, or phosphoric acid groups like salicylic and para-aminobenzoic acid interacts with the cationic surfactants. Cationic surfactant form complex with the water-soluble polymers containing the negatively charged groups as natural gums like acacia, agacan, agar-agar, carrageenan, alginate, sodium carboxymethyl cellulose, and carbachol. So these are the different behavior of different types of surface active agents. So in micellar solubilization, the inverted micelles formed by oil soluble surfactant which dissolve in a hydrocarbon solvent can solubilize water soluble compound which is located in the center of the micelle out of contact with the solvent. Micelles of non-ionic surfactants like queen, span, etc. consist of an outer shell containing their polyethylene group moieties mixed with the water and an inner core formed by their hydrocarbon moieties. So these are the mechanisms for different type of surfactants which can form the different micelles. Some compounds like phenols and benzoic acid form complexes with polyethylene glycols by hydrogen bonding and are more soluble in liquids or intermediate polarity like ethanol or ethyl ether than in liquids of low polarity like aliphatic hydrocarbons. So these compounds locate in the aqueous polyethylene glycol outer shell of non-ionic micelles on solubilization. Drugs which are soluble in oils and lipids can be solubilized by this mechanism of micellar solubilization. So, age micellar solubilization depends on the existence of micelles. It does not take place below the critical micelle concentration. So, dissolution begins at the critical micelle concentration. Above the critical micelle concentration, the amount solubilized is directly proportional to the surfactant concentration because all surfactant added to the solution in excess of CMC exist in micellar form. As the number of micelles increases, the extent of solubilization process or solubilization also increases. Compounds that are extensively solubilized increase the size of micelles in two ways. First one is the micelles swell because their core volume is augmented by the volume of the solubilized aid. And the second is the number of surfactant molecule per micelle increases. Now, lastly, the applications of micellar solubilization. So, micellar solubilization is a powerful alternative for dissolving hydrophobic drugs in aqueous environments. Because of its amphiphilic nature, micelles are known to play a vital role in many processes of interest in both fundamental and applied sciences. Micellar systems can solubilize poorly water-soluble drugs and increase their bioavailability, and they can be used as a model system for biomembrane as well as the drug carriers in numerous drug delivery and drug targeting systems. Molecules are known to have an anisotropic water distribution within their structure. In other words, the water concentration decreases from the surface towards the core of the micelle with a completely hydrophobic or water excluded core. So consequently, the spatial position of a solubilized drug in a micelle will depends on its polarity. Non-polar molecules will be solubilized in the micellar core, whereas the substance with intermediate polarity will be distributed along the surfactant molecules in certain intermediate positions. Surfactants like sodium dodecyl sulfate are used as excipients and usually added to the formulation to facilitate the preparation, patient acceptability, and functioning of the dosage form. So now when we go through the pharmaceutical application of special application of solubilization in pharmacy, we can find that the solubilization of phenolic compounds like cresol, chlorocresol, chloroxylenol, and thymol with soap to form clear solutions for use in the disinfection. Solubilized solution of iodine in non-ionic surfactant micelles, which is known as iodophos, can be used in the instrument sterilization. Solubilization of drugs like, for example, steroids, water-insoluble vitamins, essential oils by non-ionic surfactant usually contain polysorbates or polyoxyethylene sorbital esters or fatty acids. So this can be done with the help of solubilization mechanism. These are the references of today's lecture. So in summarized form, we discussed about the hydrophilic, lipophilic determination of surface active agents. Then we discussed about the detergency and its mechanism. And lastly, we discussed about the micellar solubilization, its mechanism in detail. And finally, we discussed about the applications of solubilization in pharmaceutical sciences. So this is about the today's lecture. These are the different references. You can go through these references and find out more details about today's topic. And lastly, after completion of after reading of all these things, you can be capable to answer the different questions like what is HLV value required for surfactant functions is wetting agents. What do we mean by micelles? What is detergency? Define solubilization. What is CMC? Next question is give the applications of solubilization in pharmacy. Write the examples of detergents, different examples of solubilizers, different examples of foaming agents, and lastly, what are the emulsifying agents. So after completion of this lecture or today's lecture, I hope you may be capable to give the answers of these questions. So now, thank you.